What's up to you all grade 11 minds? It is pre-matriculants. Welcome to your favorite show. It is Learn Extra Live with me, Abram, and Mr. John. John, how are you?
Very good, thanks, Abram. Are you doing well?
I'm doing well, but I'm a bit scared now. What's happening?
Hey, listen, guys, we're going
to be a Chinese.
No. This isn't about. Hey,
all right,
we're not on Maths Lit, eh? So, if you don't know, the other day we had some coloured spray in people's hair, but it was Chinese and didn't really play up very well. Now, I've got a little problem for you. And I know that you're really into your graphic design.
Yes.
So here's one for you to think about. Challenge question for Abram. Maybe you'd like to try it at home as well. If I've got two things, okay, two sticks, how can I arrange them so that they're the maximum angle apart? Okay, you'll agree two things is easy. The maximum angle is 180 degrees.
Yes.
It's not a trick question, Abram. Okay, so if I had three things, graphic design will tell us that we can take 360 and we can break it apart into 120, 120, 120. Okay, agree?
Yes.
So my challenge to you is, what's the maximum arrangement, angle, that you can arrange four things in space? Okay, so I'm going to let Abram think about that while we're doing our stuff. But before he gets going, he better tell you some stuff, otherwise we'll never get going. So you go for it.
First things, my sisters, you need to download your notes. They're all for free on learn.mindset.co.za. Second thing, if you're struggling and if you have some comments that you have about the show, feel free to post them on facebook.com/learnextra. Like the page, share the page with everybody, your friends, your family, everyone. Let them learn more and learn extra with us on Learn Extra. That is the page, and your teachers also, they must be on the page to help you and also help other students. But otherwise, on Twitter, you can follow us at Learn Extra. And now we have posted the challenge question. It's on our Facebook page. You feel free to try it out, mindsetters. But above it all, John, to wrap it, we have a campaign that we're saying we're working together with the mindsetters. We're a family that likes to be part of other families, and we like everybody to be within our family.
Absolutely, and that's why we want to walk together.
Exactly.
That's our campaign at the moment. And guys, we're not just stopping this after term one. What's the point of starting to walk together? No, we want to walk all the way to the end of the year and beyond. So you're committed. You're part of the tribe. You're part of the team. Let's make it work.
So true. It's all about keeping the momentum from the start up until the end. So mindsetters, this has just begun and will be with you throughout the year until the last day. But all you need to do is to caption the picture that we have posted on Facebook. Tell all your friends about that caption. Let them like it. Because if your comment has the most likes, you'll get an opportunity to win an awesome Tommy Takers, a pair of your choice, with the color of your choice, of course. But for now, John, what do you have for us?
Okay, I want to get that caption because I don't think many people have seen it. So just give me a second while I find it. There we go. Is that it? Is
yes,
that the one?
That's the one.
Okay, so guys, there you go. I hope you can see it. It's a little caption. It's down towards the bottom of the post. We'll post this up and pin it to the top as soon as the grade 12 lesson is over. So please don't go away. Later on tonight, get that post up and go and look at the captions. There's some great captions happening already. If you can think of another one that relates to this, with tackies and the word us in the middle, about doing something together. Maybe 1 + 1 = 3. I don't know. Something like that. Well, that's with Abram's calculator. The thing is, go and look at the comments. Like the comments. Share. Get your friends to like your comment. Get more people to get onto the page so that more people can learn and work together. Last thing that I want to just show you on the page, apart from the challenge question, and I'm scrolling up very quickly, there's your challenge question, and we'll come to it in a minute. What I want you to do is to post your answers underneath as a comment. And the final thing just to look at is, hey, Abram, have you noticed? We're almost at 800.
Wow.
69,800. Guys, that's 60 to go. Before we had 69,800 to 800, and it's only another 260 to 70,000. Hey, do you think we could get there by the end of this week?
By the end of this show, I trust the
No.
mindsetters.
At the end of the show, maybe a bit of a push, but end of the week, guys, let's see if we can get to 70,000. I think we could have something special on the last show on Thursday if we can get to 70,000.
I like that.
A
You're full of
cake or
surprises,
something.
John.
Eh? Yeah, a surprise, guys. But it's time for you to get sharing, liking, get your friends onto the page, and let's get working as well. Because what we're doing today is we're talking about molecules. We're talking about chemistry. We've been dealing in grade 11 with physics for most of the term. Now it's time to get explosive with some chemistry. So let's do some revision about atomic combinations, about molecular structure. Now, the challenge I gave to Abram earlier wasn't just a fun thing because I know he likes to play with sticks and likes to do some design, but it's a very serious question. And it's very important. We're going to ask him for his solution just now. But let's get on and see what we're going to deal with in today's lesson. We're going to identify and describe the shape of molecules. Look at different molecules. Remind ourselves how atoms join together. The notes about different types of bonding are on the page, and we'll have a little bit to say about that. We're going to discuss the forces between molecules, which we call intermolecular, between molecules, and we're going to discuss how intermolecular forces affect physical properties of substances. And this is fascinating. It's not only fascinating, but it's really important. If you've got a buddy in grade 12, then you better get them watching this show as well. Because the section that we did last week in organic chemistry for grade 12 is very relevant to this idea. So you need to mark this as a grade 11 section. I must know for grade 12. It's examinable. And we're going to link it to organic chemistry. Even though in grade 11 we don't do that much organic chemistry, and it's not examinable, but the ideas are there and we need to know them. So let's move on. First thing, challenge question. Are you up for it? Abram's got a challenge. How are you doing with your challenge? I see you've given up already.
I have my solution, John.
You have your solution.
Yeah. Tell them about their challenge question,
okay,
and then come back
we'll
to
get
my
your solution.
Yes.
Okay. So it says, explain why at room temperature, 25 degrees Celsius. Okay, 25 degrees Celsius. That's room temperature. Explain why fluorine is a gas, bromine is a liquid, and iodine is a solid. Just to help you and give you a little bit of a hint, I've got the periodic table here, and I want to show you that that's where those elements are. Fluorine is over there. Then we've got bromine over there, and we've got iodine down below it. So we're looking at group 17 on the periodic table. Group 17, the halogens. We're asking, why does it start with a gas, then go to liquid, then go to solid? Interesting question. Have you got your solution?
Very interesting. This is what I think, John. I'm thinking this is going to be 90 degrees.
Abra.
So it's going to be,
Yeah,
it's going to be 90
yeah,
and 90
yeah,
and 90, 90
yeah.
and 90.
Okay, guys.
That's what I'm thinking.
The majority of people will give that solution. And guess what? It's wrong.
Or maybe we can just put it all flat and then get 180.
No. I want them joined at one central point.
Okay.
I want them joined at one central point. Okay. The majority of learners, the majority of people out there will tell me that the answer is 90. I'm going to say to you, think again.
Okay.
That's your first attempt. I'll give you a clue a little later if you aren't on the right path. Okay? But for the moment, let's get on with the summary. Okay, so here we go. First thing I want to talk about, do a bit of revision. And the important thing here is that there's some terminology that you need to know. You need to know the difference between an element and a compound. So we're doing some grade 10 revision very quickly. What we recognize is an element. Those are simple substances. They are pure substances, and they have special properties. They are listed on the periodic table for us. We can't make them simpler. So if you get some gold, you can't refine it and make another substance out of it. Even if you break it apart, the smallest bits will just break into 2 bits of gold. So imagine you had a lump of gold and you took a very thin knife and you cut it into a very thin shaving. You would still have gold. It would have all the properties of gold. You can't make it a simpler substance. So it's the simplest substance, that's an element. A compound is a chemical combination of elements. So this is a combination. And it's a chemical combination. Usually requires heat of elements. So what happens is we start with some elements, we join them together, and we react them, and we get a bang, and we make a new substance that has different properties to the elements. I've been very careful in my terminology. This is a simple substance. It's a pure substance. Simple, pure substance that can't be broken down. You can't break down. Cannot break it down. Can't make it simpler. These ones, compounds, you can break them down. You can make them into elements. You can decompose compounds to make elements. We can do this with electrolysis. We can do it with heating. We can break them down. What we can do with elements is if we try and do anything, we make compounds. We join them together. We take elements and we react them together. The elements are the reactants, and the product is the compound. Okay? This is known as a synthesis reaction. This is known as a decomposition reaction. Now guys, very, very important terminology. What we need to understand the process of both synthesis and decomposition, we've got to understand what's happening at a microscopic level. The microscopic level, there are changes that are happening, and we need to describe matter in terms of particles. And generally, the most important thing that we can say here, and it's the link that I want you to get, all elements, their simplest particles, their particles in fact, are called atoms. Okay? So elements are made up of atoms, but compounds are made up of molecules. Now, that's a very important thing. Molecules, atoms join together to give us molecules. There are just 2 exceptions that I want to talk about. It's true that these are made up of atoms, but we can sometimes get the same atoms joining together, and even not joining together. We get the things called the noble gases, and these are just atoms. They never bond. No bonding. They do not bond. No bonding takes place. And we call these monatomic molecules. Example, helium, neon, argon. Those are monatomic molecules. They don't bond. Then we get diatomic molecules, and that's the group that we were talking about. We get things like hydrogen, we get things like fluorine, chlorine, bromine. Notice, diatomic. What do you think that means? 2 atoms in each molecule. And you even get things called triatomic and more. So we can get bigger things like phosphorus, P4, and sulfur, S8. These are molecules that form when we have atoms on their own. So molecules can be used for elements as well as for compounds, but it's joining things together. Last thing that I want to just say for you at the moment, this joining together takes place in two ways. We can either have a sharing of electrons of the atoms, that's known as covalent bonding. That's very common with nonmetals. Or we can have a transfer of electrons. This is called ionic bonding. Now, we're going to have a lot more to say about these different types of bonding. But for the moment, we're going to focus on covalent. We're looking at structures of molecules. Okay, Abram, have you come up with another solution? Bigger than 90 degrees.
I'm working on it, John.
You're working on it.
Yes.
Don't take too long, but I think it's time for a break now.
All right, so I'll work on it during the break.
Good.
Right, before we take that break, Mindsetters, I just want to send this shout out. Best Killed Jomo Libya says, I've made my whole class to watch Mindset, ha ha ha. A big shout out to Mudubatse High School kids for me. So if you're tuned in from Mudubatse High School, a big shout out to you, and tell also other classes to tune into Mindset. Otherwise, Mindsetters, if you are also watching in groups, let us know on facebook.com/LearnExtra. We'll see you after this break. Welcome back, grade 11s. If you just joined us now, you're a bit late, but do download your notes on land.mindset.co.za. And if you're struggling, send your questions through on Mindset's Facebook page, which is facebook.com/LearnExtra. I'm here to help you even on Twitter @LearnExtra. John?
So how are you coming on with your challenge?
Okay, this was my first solution, of which
was 90-90-90.
Which was 90-90-90.
Okay.
And my second solution now, I think it's a bit, it's getting there. I think I'm getting there. And I'm left with this one now.
Okay.
In a way.
Okay. So what I said, and I saw Abram was struggling a little bit, and so I want you to think about it as well. The moment what Abram's doing is he's trying to get them not all on the same plane, okay? He's trying to move them out of the plane, and that's really clever thinking, because that's where the solution is. Why are we doing this is because the shapes of molecules determine their physical properties. Remember I said to you a molecule before the break is a combination of atoms. The shapes of molecules will determine their physical properties and how they make up substances, which goes back to our challenge question. So let's understand a little bit about shapes. And I'm going to just go through something that you will have done possibly at school. We'll look at some shapes. First shape that we'll look at is linear. That means straight. And we can understand it by looking at the Lewis diagram, counting up the bonding and non-bonding pairs, and recognizing that you've got that shape. So you can revise that. You can also get things that are angular. They're still linear. They can even be flat, three things spread apart as far away from each other. You can get something that's called pyramidal, and then you can get a tetrahedral. Now, I'm going to use those shapes to try and answer this question. And it says, determine the shape of the molecules of methane, ethane, ethene, and ethine. Now, guys, you don't need to know the naming conventions, although they are quite easy and you'll learn them in grade 12. But all we have to do is look at the bonds that are formed. And the important thing here that I want to start off with is just recognize where carbon is on the periodic table. And so we'll look at carbon and we'll see carbon is the 6th element, and it's in group 14, and it has 1 valence electron, 2 valence electrons, 3 valence electrons, 4 valence electrons. So when I draw the Lewis diagram of carbon, what I'm going to do is I'm going to say, there's the Lewis diagram like that. And for CH4, it won't be difficult to recognize that that's the structure that I can draw as the Lewis diagram. Lewis diagram, simply showing the valence electrons and showing it as a flat arrangement. What I want you to recognize is that these are bonding pairs. They are sharing electrons. And they're sharing electrons, in this case, unequally, because carbon has a higher electronegativity number than hydrogen. Check it on the periodic table very quickly, and you'll see that carbon, just erase it because I've done it over here, carbon has an electronegativity number of 2,5, and hydrogen has an electronegativity of 2,1. Now, the difference in electronegativity, 2,5 minus 2,1, is equal to 0,4. And this is a weak polar bond. It's not very strong. It's unequal sharing, but it's not totally unequal. Abram, please, won't you come here so that we can do a little experiment.
I'm coming with my solution.
Are you coming with your solution as well? Okay, excellent. Let's see. So what have you got? This, notice, this angle here, and this angle here, and this angle here, and this angle here can all be equal to each other. It's 109,4 degrees. It's the angle for a tetrahedral. Now, I promise you, Abram didn't get the answer from me. He might have Googled it. He might have looked it up on the interweb. Or he was being creative. I'll take it that
and also the clever director, because we gave us some clues.
Okay,
we worked on it.
We worked on it. Well done, Belinda. Well done, James. Well done. It's a perfect solution. It's a very important solution. Now I want you to do something with me here. Give me one of those sticks, just one. Okay, and hold on to the other end. And we're going to be nice to each other. Okay? We're going to pretend that we're equal masses. Now, we're not actually. I wish we were, or I was a little less. But
I was a little bit more.
No, we don't want Abram to be a bit more. But guys, at the moment we're sharing equally. Okay? This is what happens when we have non-polar covalent. Now, watch what happens when I am the bully. I take more of the stick. Can you see? Abram has to give more of the electron pair to me. If this was an electron pair, the electron pair is closer to me, further away from Abram. Over here, they were equal. What's going to happen if they're closer to me is my side of the molecule, if Abram is an atom and I'm an atom, then my side of the molecule is going to be more negative. Abram's side is going to be more positive. You got that? That means this molecule will be polar. When there's unequal sharing, we can get a polar type bond. Polar bonds form when the electronegativity number difference is greater than 1 or 1, and if it's greater than 1,7, this is what happens. I take both pairs of electrons, I become negative, and Abram becomes positive. But what happens to positives and negatives? What happens when you've got a positive and a negative?
They're apart.
Huh? Do they pull apart?
They pull apart, yes.
Positive and negative?
No, they attract each other.
They attract each other, yes. This is called ionic bonding. Okay, so there you've got the 3 examples of different type bond. Let's revise them. Equal sharing, like mind-setters do. We share equally all the time. Non-polar. Polar, okay? The more it's to my side, the more polar it is. If it's weakly polar, it'll just be a little bit on this side. If it's equal, it's halfway the distance. If I get it all, it's ionic. Got it? Okay. Thanks, Abram. I'm going to need you just now. Well done on getting that solution. We're going to use it now. So, as I said to you, we're going to use this solution because we know this is not the right shape. The theory that gives us the right shape is a theory called VESPR or VSEPR. And simply what that means is it says pairs of electrons want to get as far away from each other as possible in space. So I'm going to answer the rest of these questions now by doing a little modeling exercise. And this is something that you can do at home. You might not use the same things as I'm going to use, but I hope it makes it clear for you. So follow me. Let's go and have a look. Okay, so here I am. It's not a cooking show. We're doing some chemistry models. And what I'm going to do is I'm going to take a marshmallow like this, and I'm going to represent this as the carbon atom. And I'm going to say one carbon atom needs to have some partners. It needs to have some hydrogen partners. The hydrogens are smaller, so I'm going to break the hydrogens apart, and I'm going to do like that. So there I've got one carbon and 4 hydrogens. Let's see if we can get Abram's model to work. So there we go. There's one bond. Okay, got it. Next bond, we're going to stick it in over there like that, and we're going to stick the hydrogen on top of it. So you've got that one in like that. Then we're going to do the next one and stick it out here. And the last one, the last hydrogen, we're going to stick over here. Now, the thing about a perfect tetrahedral, and I've just done this very quickly, is that it doesn't matter which side is up. It will be symmetrical. Isn't that amazing? Mm. Okay? So this angle, this bond angle, will be equal. Doesn't matter which way you look at it. It will always be the same. And it's quite a cool little model like that. It's not going to stand up for me. I hoped it would, but it's just looking like it's flopping down. So I hope you can see the shape of the tetrahedral. Lots of molecules have this shape, and it's a nice 3D model. 109,4 degrees. Got it. Okay, next one that I want to deal with is ethane. Okay, ethane, I need 2 carbons, 2 of these, and I need how many hydrogens on the board there? Just read for me. Ethane, 4 hydrogens. Is that right? Can you read for me?
Yes.
6 hydrogens.
Yes.
No. Okay, let's get ethane, 6 hydrogens. So we're going to get, thank you, just breaking the marshmallow apart. Are you hungry, Abram?
I have.
You're seeing all this.
I'll take the leftovers.
You'll take the leftovers. Let me be kind to you. You can have one now.
Thank you.
Okay, there you go. Abram's got his marshmallow. He's had it. We'll have a look at what happens next. Okay, so the first thing that we need to recognize, we've got a carbon-to-carbon bond. So there's my carbon-to-carbon bond. Okay, guys, very, very important. It's the strongest bond, and as I've illustrated it, we could change the length of these bonds. The carbon-to-carbon bond should really be shorter than the carbon-to-hydrogen bond, but notice that this carbon here is going to have 3 hydrogens sticking out from it. How do you think those 3 hydrogens will go? Well, just like the others that we had. When we've got 3, they're going to be in a tetrahedral. So the one is going to go in there. They want to get as far apart from each other as possible. So, oh, this stick isn't very good, so I'm just going to throw that one away. I don't know what happened there. Bamboo from China didn't work too well. And we're going to take another one and stick it in over here. Now we need to be careful that we're not going too flat. We need to make sure this is still tetrahedral. And that's the whole important part of this lesson, is to show you that on the ethane molecule, it's still a tetrahedral because we've got 4 things in space. What do you think is going to happen on this other side? Well, we're also going to get 4 things in space shifted over there. Abram, I might need your hands here because it looks like this is flopping a bit. So I'm going to turn that one around. Can you just hold there? And we're going to now stick this in. And we're going to stick the last one in over there like that. Excellent. So guys, do you notice something? That there's a carbon and 3 hydrogens on the left and a carbon and 3 hydrogens on the right. That's quite cool, huh? But you also notice that in space they've arranged themselves that this one is down, and on this side, on the left, on my left-hand side, there are 2. And on this side, on the right-hand side, there are 2 up, and on my left, there's 1. So they've got as far apart from each other as possible. Okay? The bond angles are all 109,4 degrees. It's a special, very special angle, the angle of a tetrahedral. Now, I could waste some more marshmallows, but I'm going to ask Abram to help me here, because I want to take away 2 hydrogens. Take the top 2 hydrogens away. Just pull those sticks out. Okay. Now, what I want you to see is the next molecule has 2 less hydrogens. But what happens is we now get a different shape. What happens is the carbons join together with what we call a double bond. Okay? And I've put 2 bonds in there. And now what do you think is going to happen to this bond angle? First of all, I hope you can see that it now becomes more difficult to rotate. It's more firm. The structure is more. What do you think this angle between here and here is going to be? Is it still going to be 109? Do you think it's going to move further apart?
No.
Yeah.
Just a bit, John.
Okay. So exactly now what you've got around this thing is 3. 1, 1, 2, 3. And we're lying flat, and we go to 360 around a point. So what's 3 divided by 360?
It's 120.
120. That's exactly it. So this molecule, guys, C2H4, which is ethene, is 120 apart. Okay. I want to keep that to one side, because we're going to come back to that a little later. Now, the last one that we're going to do, we just move through very quickly, is we're going to put 3 bonds between carbons. Okay, 2 carbons, 3 bonds. Okay, how many bonds are left over? Remember, carbon has 4 bonding pairs, 4 valence electrons. So we've taken 3. This is for ethine. In your notes, you will see ethine is C2H2. So what's missing?
Hydrogen.
Hydrogen. How many hydrogens?
2.
Okay, 2. This is really useless, so I'm going to use it, because you've got to use the useless things in life as well. And we're going to take 2 hydrogens. We're going to put 1 on this side. Is it far away from that carbon? Angle-wise?
Yes.
No, look,
yes.
It's 180 degrees. And on this side, what can we do? Another hydrogen. Okay? Got it? See what it is? It's now a linear molecule. So we've got linear, the planar molecule, and the tetrahedral. Guys, I hope that's helped you to see these molecules. Go and build them for yourselves. I'm needing to get back to the board, so perhaps you'd like to. No, you can't. No. Off you go. You've had your marshmallow. Abram. What will I do with Abram? You know, he does really not always behave so badly. But anyway, so let's go and make sure that we've got this right now. So the shape of the molecule, I just want to give the answers. This is a tetrahedral. This is also a tetrahedral. This is a planar or trigonal planar, and this is a linear. Guys, I hope you followed that very carefully, and that you can see by arranging the molecules as far apart from each other that it's actually a lot of fun. Follow the pattern and make sure that you identify lone pairs, bond pairs, spread them apart as far as possible. Makes for a very interesting science. Abram, over to you.
Thank you so much, John. And that's very good news. I'm going to have my Milo during the break. But otherwise, my sisters, do send us your questions and do try out the challenge question that is posted on our wall on facebook.com/LearnExtra. See you soon. Welcome back, Mindsetters. Now back to you on Facebook. Let's check what you guys are saying. There's an awesome comment from Sanele saying, hey, Mindset Team, I'd like to send a big shout out to every grade 11 from Educational Life School who is watching this wonderful show. I love you all. It's such an awesome show. Keep it up, guys. And Tabiso, me and my friend Peter always discuss the show every day in class. I'm from Mudubatse High School, Abashwe. And hi, John, I'm hungry.
Oh, I tell you what, if we could send an electromagnetic wave and let it carry a marshmallow, we'd send it to all of you. But unfortunately, electromagnetic waves only carry television, and radio don't carry food. Sorry about that.
All right, can I just say one last more,
Yes.
John? Steve Makhweleho says, hi Mindset, help me. I'm watching TV Mindset with my family, and I wish you can say my name on TV. I want to make my parent happy with me. So I just said your name, Steve Makhweleho. Hi.
Hi, Steve. Great to have you. I hope you're not from Beep Bank.
Why?
No, just that advert. Let's get on to the challenge question. Now, guys, I see there's lots of excitement about the challenge question, and I'm really excited too. So, and I've been going through a couple because it says, as we've mentioned, explain why fluorine is a gas, bromine is a liquid, and iodine is a solid at room temperature. And there's some great questions, but there's also something that I noticed that comes from Malinga. Sorry if I've pronounced your name incorrectly. He says not everyone has smartphones that can access the graphics. So guys, what I'm going to ask Abram to do is tomorrow he's going to try and find out what phones you have. So he's going to be posting some stuff on different types of phones because we really want you to get the best of our information with the devices that you've got. But sometimes we don't know. Maybe, so look out on the page. There'll be some things for you to like and share so that we can get some data because we really don't want you to miss out on because we don't know. So we'll try and structure things so we can meet the majority and make sure that everyone gets as much information as they can. I've seen some great answers, and the list carries on and on and on, and that's really fantastic. But now let's go and get the solution. The other thing, Abram, that I've noticed is that these grade 11s, the pre-matriculants, they're liking the page. Look, we've only got 20, how many?
28.
28 to go. 28 before we get to 69800. 69800. Can we get there tonight? Get your friends to like the page and let's see how we go. Right, let's go to the answer to this. So the answer that I would start with is as follows. We need to recognize, as I mentioned earlier, that these are all halogens. So the first thing is we recognize they're all halogens. And if they're halogens, they're all diatomic molecules. Why do I say that? Because look, fluorine has a valency, has a Lewis diagram that looks like this. It has how many is that? 7 valence electrons. And when I take another fluorine atom with 7 valence electrons, and I now take these fluorine atoms and I pull them together, they can share electrons like that, and they are sharing that pair of electrons equally. So there's equal sharing, because one fluorine pulling against one fluorine is going to share equally. It's not like little Abram and Big John, okay? It's not like that. It's not they share equally. They're kind to each other. So this forms a non-polar molecule. And if it's a non-polar molecule, it will do the same for all the others. Okay? So all the others, fluorine, iodine, bromine, chlorine even, they will all be non-polar molecules. So what we need to now recognize is, I'm going to draw a different picture. There's one non-polar molecule, there's another non-polar molecule. Non-polar means the electrons are equally distributed. Okay, equal distribution. So there's no end that is positive and no end that is negative. I want to just show you in this model what a polar molecule would look like. A polar molecule would look like this. Okay, where this end is slightly negative and this end is positive. That would be a polar molecule. Now, what can you tell me if a polar molecule met another polar molecule? Well, you'd say, like we said earlier, opposites attract. So on the other side of this, if there was a little delta positive over here, there would be a force of attraction between them. That type of attraction is known as van der Waals forces. We haven't got that happening here. These are equal distribution of electrons, but the molecule's outer area is all negative. So this one moving to this one, they will repel each other. Problem comes, and I'm going to try and do this, is if I select that one, and I'm going to try, I don't think I've got everything. I want the whole line. No, I've not got what I want. What we would recognize is as those things move closer together, there can be a little bit of what we call an induced movement of electrons. So, Abram, have you ever been sitting quietly doing your work and somebody comes and says, boo?
You just did now.
Okay, I almost did. You didn't catch him quite on TV doing it. But if I did, and I jumped my foot and did that, he might do this and jump out of his chair. I haven't touched him. I'm at a distance, but I've induced a reaction. Okay? So there's a temporary induced dipole. What this means is very quickly, is under a few seconds, just for a little while, and I hate the fact that it's picking both of those. I don't want it to do that. I just wanted to do those. These ones run away. They run to that side. So just for a second, this becomes a little bit of a negative region. This becomes a little bit of a positive region. If this becomes a little bit positive, then all the electrons on this side are going to want to run there. So these ones are going to want to go there, making this a little bit negative and this a little bit positive. And so now we've got the non-polar molecules. They become temporary induced dipoles. We call this London forces. We say there are London forces between these molecules. But notice, it's temporary and it's induced. Doesn't stay for the whole time. They are generally very weak. But here's the point. The more electrons I've got, the more I jump, the more scatter I will make. If you've just got a little puddle and you throw a stone in, you won't get a big splash. If you've got a big puddle and you throw a brick in or throw a stone in, you'll get ripples running through the whole thing. Same thing happening here. So the more electrons, the bigger the temporary induced dipoles are, the stronger these intermolecular forces will be. So let's go back to it and let's have a look. Fluorine on the periodic table, let's go to the periodic table, has 9 electrons. That's in the molecule 18, because I'm doubling it up. Chlorine, bromine has 70, Br2 has 70 electrons, and iodine, I2, has 106 electrons. Can you see that's many more? So the more electrons, the stronger these temporary induced dipoles will be. And if there are stronger intermolecular forces, then the phase at room temperature will change. The force of the molecules will pull each other together. They'll become tightly packed. Tightly packed means they'll be solid. So big number of electrons, solid. Quite a big number, but not so big. Liquid. Small number of electrons in the molecule, that remains gas, because the intermolecular forces are generally quite weak. Abram, I think I've answered the challenge question, but I know there are lots of questions on the page. So
Yes,
let's try and get some of those done as quickly as we can.
And big ups to everybody that has tried the challenge question. Here's a question from Msanga. How does the structure of an octahedral look like?
Okay, an octahedral. Now, guys, octahedral, It's got 4 out this way. So it's in 4 that way, 1 up that way, and 1 down that way. Okay? So we haven't got a really nice drawing of it, but it's something that has got 6 central atom with 6 things sticking on it on the outside. I hope I've explained that okay. So it's 4 in the middle and 1 up and one down. Okay.
All right. How do you identify a bond molecular shape?
Okay. The whole process is called VSEPR. The principle is that you take your molecule, you take your central atom. So there's always a central atom. So like CH4, that's the central atom is carbon. And we draw the Lewis diagram like I did. So we always do this. Always draw the Lewis structure. It doesn't matter which one it is. And then you count the number of bond pairs. So draw the Lewis diagram, count the number of bond pairs. Let me do another one. So because we've done that one, let's take water. Very famous one. Oxygen, valence, electrons look like that. And please forgive me for not explaining everything. But the valence electrons of oxygen, there are 6 of them. They've got 2 bond pairs. So there are 2 bond pairs. There's a second one. These ones are lone pairs because they've only got the electrons from the oxygen. We know those as lone pairs. Okay? So how many pairs of electrons have we got around the central atom? Or the central, it's 4 pairs. Okay? So there are 4 pairs, but 2 of them are bond pairs, 2 of them are lone pairs. So the basic structure here will be tetrahedral. So because of the number of pairs, we're going to start off with a tetrahedral. But the problem is these lone pairs. They repel each other more than if they were bond pairs. They open up, and the end result is that we don't take the shape including these ones. We take the shape just from the oxygen and the bond pairs. And so we say that this shape with the 2 lone pairs, this collapses a little, and it gets down to a very special angle. It's about 104. It's in that region. I haven't got it off the top of my head. I think it's 104,3 degrees. It pushes down like that, and we call this bent or angular. So you've really got to go through the process, count the number of pairs, and learn the summary table. Identify the specific ones that you got in your textbook, the ones that are in the notes as well. Okay.
Thank you so much, John. I must end the show with this comment from a teacher.
Yes.
Zotile Mve says, "Hi, may you please read my status on TV? I'm an educator teaching physical sciences in Bergville, Ngqongqozi High School. I love this show. I also learn from it. I would like to wish all the grade 12 learners a good luck as they're about to write their March paper." Thank you so much, Zotile. Really appreciate hearing that from an educator.
Excellent. Well done, and thank you so much. We'd love to share with you as well. So comment on our page, help the learners, and get your learners to watch and like our page too.
Awesome. Thank you so much, John. Big John. It's been a great pleasure working with you as little Abram. My sisters, thank you for watching, and thank you for sending your questions and sweet comments on our Facebook page. Keep them coming. We love you. Until next time, peace. What's up to you all grade 11 Mind Cities pre-matriculants? Welcome to your favorite show. It is Learn Extra Live with me, Abram, and Mr. John. John, how are you?
Very good, thanks, Abram. Are you doing well?
I'm doing well, but I'm a bit scared now. What's happening?
Hey, listen, guys, we're going
to be a Chinese.
No. This isn't about. Hey,
all right,
we're not on Maths Lit, eh? So, if you don't know, the other day we had some colored spray in people's hair, but it was Chinese and didn't really play up very well. Now, I've got a little problem for you. And I know that you're really into your graphic design.
Yes.
So here's one for you to think about. Challenge question for Abram. Maybe you'd like to try it at home as well. If I've got two things, okay, two sticks, how can I arrange them so that they're the maximum angle apart? Okay, you'll agree two things is easy. The maximum angle is 180 degrees.
Yes.
It's not a trick question, Abram. Okay, so if I had three things, graphic design will tell us that we can take 360 out. Chemistry. We've been dealing in grade 11 with physics for most of the term. Now it's time to get explosive with some chemistry. So let's do some revision about atomic combinations, about molecular structure. Now, the challenge I gave to Abram earlier wasn't just a fun thing because I know he likes to play with sticks and likes to do some design, but it's a very serious question. And it's very important. We're going to ask him for his solution just now. But let's get on and see what we're going to deal with in today's lesson. We're going to identify and describe the shape of molecules. Look at different molecules. Remind ourselves how atoms join together. The notes about different types of bonding are on the page, and we'll have a little bit to say about that. We're going to discuss the forces between molecules, which we call intermolecular, between molecules, and we're going to discuss how intermolecular forces affect physical properties of substances. And this is fascinating. It's not only fascinating, but it's really important. If you've got a buddy in grade 12, then you better get them watching this show as well. Because the section that we did last week, the thing is, go and look at the comments, like the comments, share, get your friends to like your comment. Get more people to get onto the page so that more people can learn and work together. Last thing that I want to just show you on the page, apart from the challenge question, and I'm scrolling up very quickly, there's your challenge question, and we'll come to it in a minute. What I want you to do is to post your answers underneath as a comment. And the final thing just to look at is, hey, Abram, have you noticed? We're almost at 800.
Wow.
69,800. Guys, that's 60 to go. Before we had 69,800 to 800, and it's only another 260 to 70,000. Hey, do you think we could get there by the end of this week?
By the end of this show, I trust the mindsetters.
At the end of the show, maybe a bit of a push, but end of the week, guys, let's see if we can get to 70,000. I think we could have something special on the last show on Thursday if we can get to 70,000.
I like that.
A cake or something. Hey? Yeah, a surprise, guys. But it's time for you to get sharing, liking, get your friends onto the page, and let's get working as well. Because what we're doing today is we're talking about molecules. We're talking about, and we can break it apart into 120, 120, 120. Okay, agree?
Yes.
So my challenge to you is, what's the maximum arrangement angle that you can arrange 4 things in space? Okay. So I'm going to let Abram think about that while we're doing our stuff. But before he gets going, he better tell you some stuff. Otherwise, we'll never get going. So you go for it.
First things, my sisters, you need to download your notes. They're all for free on learn.mindset.co.za. Second thing, if you're struggling and if you have some comments that you have about the show, feel free to post them on facebook.com/learnextra. Like the page, share the page with everybody, your friends, your family, everyone. Let them learn more and learn extra with us on Learn Extra. That is the page, and your teachers also, they must be on the page to help you and also help other students. But otherwise, on Twitter, you can follow us at Learn Extra. And now we have posted the challenge question. It's on our Facebook page. You feel free to try it out, mindsetters. But above it all, John, to wrap it, we have a campaign that we're saying we're working together with the Mindsetters. We're a family that likes to be part of other families, and we like everybody to be within our family.
Absolutely. And that's why we want to walk together.
Exactly.
That's our campaign at the moment. And guys, we're not just stopping this after term 1. What's the point of starting to walk together? No, we want to walk all the way to the end of the year and beyond. So you're committed. You're part of the tribe. You're part of the team. Let's make it work.
So true. It's all about keeping the momentum from the start up until the end. So Mindsetters, this has just begun and will be with you throughout the year until the last day. But all you need to do is to caption the picture that we have posted on Facebook. Tell all your friends about that caption. Let them like it. Because if your comment has the most likes, you'll get an opportunity to win an awesome Tommy Takers, a pair of your choice with the color of your choice, of course. But for now, John, what do you have for us?
Okay, I want to get that caption because I don't think many people have seen it. So just give me a second while I find it. There we go. Is that it? Is
Yes,
that the one?
That's the one.
Okay, so guys, there you go. I hope you can see it. It's a little caption. It's down towards the bottom of the post. We'll post this up and pin it to the top as soon as the grade 12 lesson is over. So please don't go away. Later on tonight, get that post up and go and look at the captions. There's some great captions happening already. If you can think of another one that relates to this, with tackies and the word us in the middle, about doing something together. Maybe 1 + 1 = 3. I don't know. Something like that. Well, that's with Abram's calculator.